Hello, my name is Jonathan and today I'll be giving a video presentation about my spring semester project. The project consists of two separate tasks. I'll first discuss about task 1. The first task requires us to build a facial recognition system using Python. Our goal is to not only detect but also recognize faces in real time. Our facial recognition system was constructed by making use of Agit's Gay Face Recognition API. This API, which stands for Application Programming Interface, allows us to access and make use of useful machine learning models from the DLib library. Among the two models used for our face recognition system is the feature descriptor model and the face encodings model. I'll now discuss how these two models shape our face recognition system with the flowchart below. Face recognition process is broken down into 3 stages as seen from the flowchart. Let's first discuss about stage 1. So in stage 1, face detection is done on the database and candidate photos with the help of our feature descriptor model. The feature descriptor model provided by DLib are either the HOG model or the CNN model. We decided on the histogram of oriented gradients HOG model as it's not only not computationally heavy on the computer but also provides great accuracy. After detection in stage 1, we then can move on to stage 2. So in stage 2, the face encoding process is done with the help of our face encodings model. The face encodings model is a trained deep convolutional neural network that converts the detected faces in stage 1 to a set of 128 facial feature measurements which are unique to that person only. With the encodings of faces in hand, we then can enter to our third and final stage, that is encoding comparison. The list of face encodings from our database photos is compared with the face encodings from our candidate photo. If the similarities of encodings is high, a match is then said to be found, and this is how our face recognition system works. Before we discuss about the face recognition code, I would like to mention about the folder layout used. We created two directories named known faces and unknown faces. The known faces directory, which consists of the Jonathan folder, stored the 4 images, which are our database images, whereas the unknown faces folder consisted of another 4 images, which are our candidate images. Once this is out of the way, now let's move on to the code explanation. I'll first explain the code used to recognize faces in images. So we first have to import the libraries required, which is the face recognition library, the OS library, and the CV2 library. We then declare and assign parameters where tolerance is set to be 0.4, frame thickness set to be 3, font thickness set to be 2, and our feature descriptor model set to be the hawk model. We then create 2 lists, which is the known faces list and the known names list. The known faces list store our face encodings, and the known names list store the names to those face encodings. We then load 4 images in a Jonathan folder one by one, where the face found in the image is converted to a set of 128 feature measurements that's unique by using the face encoding function. For each image, we then append the face encoding in the known faces list and the corresponding name into the known names list. We then load 4 images in the unknown faces folder one by one, where faces are located in the image by using our hawk model, so that the located faces can then be encoded. We then print the picture number and the number of faces detected in that picture. We then convert the image from RGB to BGR as we'll be working with OpenCV. We then enter the last stage for our face recognition process, where we compare 128 measurements between our database encodings and candidate encodings. If at least one of the database encodings is similar enough to the candidate encodings, a match is said to be found. We then draw a rectangle around the match and fill a frame to write the name of that person. We then can compile and run the code. As you can see, the results show correct identification of faces together with the correct matching of names. A few changes were made to the facial recognition in images code to achieve facial recognition in real time. In this section, we'll be discussing the changes made. We first initialize our webcam using the cv2.video capture function. We then redefine a new resolution as well as a rescaled frame to increase the laggy frame rate. The known faces directory is still used, but not the unknown faces directory. The unknown faces directory was replaced by the frame-by-frame images captured by the webcam. The captured frame is then rescaled to 23.5% of the original size. The rest of the operation was then remained the same. We can then compile and run the code. So as you can see, the facial recognition system is able to recognize my face correctly. We will then move on to task 2. In task 2, we are required to build a traffic symbol recognition system which is able to classify these 10 traffic symbol classes while performing additional shape counting on the wall of shape traffic symbol. After knowing the aim and objectives of the task, we then could break down the task into 3 parts. We need to train a cascade classifier to detect the traffic symbols. We need to train a convolutional neural network model to classify the detected symbol, as well as to develop a code which uses thresholding and contouring for shape counting. We then can proceed to integrate these 3 elements to form our symbol recognition system as the flowchart below. A traffic symbol in the video from the webcam will first be detected by the cascade classifier before classification will be made by the CNN model. If the wall of shapes class is detected, then shape counting will be done using thresholding and contouring. The Cascade Trainer GUI will be used to train and to create our own cascade classifier that detects the 10 traffic symbols mentioned earlier. When the training process is completed, the cascade classifier will be in the form of an XML file and will be present in the symbol recognition directory as seen here. A folder named symbol consisting of the 10 symbol folders 0 to 9 was created, where each symbol folder contained 20 images of that symbol under varying light conditions. This can actually be seen from the pictures listed here. A CSV file was created to store the list of symbol names, where each symbol name has a corresponding class ID. We will now discuss about the code used to train our CNN model to so classify the 10 detected traffic symbols. We will first import the required libraries. We then move on to declare and assign parameters. The first parameter is path, which refers to where all the traffic symbols are stored at. The second parameter, label file, which is linked to labels.csv file, which has all the names of classes. We then move on to the batch size value and assign it to have a value of 50, and steps per epoch value to have a value of 2000, epochs value to have a value of 10, where it means training process will be iterated 10 times. We then set the image dimensions to be 32 times 32 pixels, where the image is a color image as it has 3 layers, the red, the green, and the blue layer. We then set the test ratio and validation ratio to be both 0.2, which will be used for displaying of data. We first created 2 lists, which is the images list as well as the class number list. We then import the images from each class to perform resizing before appending the images and the corresponding class number into the 2 lists, and further converting the 2 lists to a NumPy array. The images were then split into XTrain, XTest, and XValidation, while the corresponding ID was then split into YTrain, YTest, and YValidation. We will then check if the number of images matches the number of labels for each data set. We will then read the CSV file. We will then display the labeled name of traffic symbol alongside the sample images of the class to check if the name of the traffic symbol and the class is correctly matched. We then check the distribution of training data set by plotting a bar chart of number of images against class number. We then perform pre-processing on the training images. This is done by using grayscaling, equalization, as well as normalization. We then add a depth of 1 and perform augmentation, which makes the images more generic by using the image data generator function. The augmented images are original images which have undergone shifting, zooming in and out, shearing, or rotating. The augmented images are then added to the X-trained dataset. Through augmentation, we can generate more data so that the model will have a better ability to classify new images. We then show augmented image samples. The Y-train, Y-validation, and Y-test matrices were then one-hot encoded. Our convolutional neural network model was then created by modifying the LINET architecture, and our model was then compiled. We then sent our convolutional neural network model for training. After the training, a few plots were made. The training and validation losses were made, as well as the training and validation accuracies. The test score, together with the test accuracy, were printed. We then store our trained CNN as a picker object named model_train.p, and it's found to be stored here. I'll be showing a few data collected that gives us an idea of how the training went. So let's first discuss about this figure. The figure 1 shows the name of symbols with regards to its class sample images. It can be seen that the traffic symbol names is categorized with the correct traffic symbol images. We then move on to the bar chart, which shows the distribution of training data for each classes. It's then said that the distribution is almost even, which is good. We then move on to the next figure, which shows the images which have undergone augmentation, and can be seen that augmentation has been done successfully. We then enter the last two plots, where the plot on the left shows the training accuracy and validation accuracy against epochs, while the plot on the right shows the training loss as well as the validation loss against epochs. The training accuracy as well as the validation accuracy generally rises to a high level, while the training loss and validation loss decreases to a low level. This indicates that our model is successfully trained and is ready to be used. We will now be discussing about the final code that's required for symbol recognition. We first import the relevant libraries, which are NumPy library, CV2, as well as the Pickle library. We then continue to declare and assign parameters. We'll be changing the resolution as well as the brightness, and set a probability threshold of 0.6. The font used will be Hershey. We then initialize our webcam by using the cv2.videoCapture function. We then proceed to import all of our train models, which are the CN model, name model train, as well as the train cascade classifier known as symbol detection.xml. We then declare functions used for image pre-processing, which is grayscaling, histogram equalization, as well as normalization. We then continue to declare the getClassName function, which allows the name of our traffic symbol of that corresponding class to be returned. The frame-by-frame images are read where the frame is converted to a grayscale image. We can then perform symbol detection on the grayscale image by using the function detectMultiscale. A rectangle will then be drawn around the detected symbol. The image of the detected symbol will then be resized and pre-processed before classification by our trained CNN model. The pre-processed traffic symbol alongside with its class ID can actually be predicted with a certain probability by using the model predict function here. If the probability is larger than the threshold value, and if the symbol detected is the wall or shape symbol, we then convert the frame to grayscale and actually perform thresholding. Thresholding is done by using the Osu thresholding, which allows the shapes to be converted to black, while everything else is converted to white. We then continue to actually find the contours in the images, which allows us to find the boundaries of shapes. We will then calculate the area of the contours. The shape of the contours were then approximated by using the CV2 .approx poly dp, which allows us to remove noises. We then draw the determined contours on the frame. If the area is between 500 and 7000, the number of vertices will be counted and the shape will then be determined. The total number of shapes are summed and displayed on the top right corner of the screen, while the top left corner of the screen will actually display its class. The classes of other symbols will also be displayed on the top left corner when detected and classified. We can then proceed to run the code to perform traffic symbol recognition as well as shape counting. So let's do so by running the code now. And let's have a look at the result, shall we? Okay, waiting for it to load. Okay, it's unloading. As you can see, our symbol recognition system is able to detect and classify the shortcut red symbol, the shortcut yellow symbol, shortcut green symbol, stoplight symbol, football symbol, push button, shortcut blue symbol, the incline measurement symbol, distance measurement event symbol. As for the shape counting, it's also done on the wall of shape symbols as seen here. If you bring it close enough, you can see there's 3 triangles, 3 circles, and 2 rectangles. Okay, so as everything is done for task 2, this brings an end to my video presentation, and thank you.